Hi everyone, this is Miss Drummond, and I made this short video just to briefly review Learning Target 5, what makes a nucleus stable or unstable, and why is that important. I also wanted to demonstrate how to make a scatter plot graph with the protons on the x-axis and the neutrons on the y-axis to help you with part 2 of the nuclear stability activity. So the purpose is to discuss what makes a nucleus stable or unstable and why is that nuclear stability important. So first, it's important to think about the forces inside of the nucleus. There are two forces inside the nucleus: the strong nuclear force, which is an attraction between the protons and neutrons, and it acts over distances less than 1/1000th of a meter. It's the strongest force that we know of in the universe, and it only happens inside the nucleus because that's the only place where the distance is small enough where the strong nuclear force can act. So it is an extreme attraction between protons and neutrons that helps to hold the nucleus together. The electrostatic force is an attraction or repulsion between charged particles, and that means that like charges will repel each other. So the protons inside of the nucleus are repelling each other, and they are pushing against the nuclear strong force. So in my little picture here, the yellow arrows represent the nuclear strong force kind of holding the nucleus together, and the green arrows pushing against that represent the repulsive force, where the protons, the positively charged protons, are actually wanting to push away from each other at the same time. So those two forces are acting against each other in the nucleus. So the role of the neutron here is it gets in the way of that repulsive force, and it helps to reduce it so that the repulsion against strong nuclear force is weakened. And if that happens, then the strong nuclear force can hold the nucleus together very successfully. So the reason that a nucleus might be stable or unstable is related to the balance of those two forces within the nucleus. So the nucleus tends to be more stable in certain situations. So for atomic numbers less than 20, so small atoms, if the proton to neutron ratio is 1:1, then the nucleus is more stable. So you can see we have a hydrogen atom here with one proton and one neutron, and it's very stable. We also have a hydrogen isotope here with two neutrons and one proton, and that is unstable. The neutrons help to keep repulsion between the protons low, and a smaller diameter nucleus will have a larger strong force, because strong force can only happen over small diameters or small distances. So that's for small atoms. For atomic numbers greater than 20, you have more and more protons in the nucleus, and so that means you have more and more repulsion, pushing the protons apart. So you need to have more neutrons to help block that repulsion and keep the nucleus stable. The problem with adding more neutrons is as you add more neutrons, the nucleus gets larger, so that contributes to the decrease of the strong force that's holding it together. So for atomic numbers greater than 20, a balance of about 1.5 neutrons for every proton tends to be a little bit more stable. If you have atomic numbers that are greater than 83, you're starting to reach the point where the nucleus is just too large. There are a lot of protons in there. There are a lot of neutrons in there. And the proton repulsion is great, and there's just not enough nuclear force to hold that nucleus together. So atoms or isotopes with atomic numbers greater than 83 definitely tend to be unstable. So the nucleus tends to be more stable in certain situations with special magic numbers of protons and neutrons. So if a nucleus has one of these magic atomic numbers, 2, 8, 20, 28, 40, 50, or 82, those even numbered atomic numbers tend to have a stable nucleus. There's also a magic number for neutrons, and those numbers are 2, 8, 20, 40, 50, 82, and 26. So those numbers are all even, and even numbers tend to create a symmetrical nucleus, meaning if you could draw a line down through the center, here you'd have the same number of protons and neutrons on one side of the line as you do on the other. You could fold it in half, and the two halves would be exactly the same. So those even numbers tend to create a symmetrical nucleus, and that allows it to be a little more stable. So in your Learning Target 5 nuclear stability activity, you were asked to take a bunch of stable isotopes, find out how many neutrons and protons they have, and then graph those neutrons and protons in a scatter plot to take a look at the line of best fit. So to do that, you would open a new Google Sheet in your Google Drive, and you can name it Learning Target 5 Nuclear Stability. You're going to create a column for the number of neutrons and the number of protons for each isotope you have. I just made up some data here. This is not the data from the lab. So you have your column with your number of neutrons and number of protons, and then you have to highlight the data that you want to put in your graph. So I highlighted those two columns. I did not highlight the names of the isotopes because I don't want them in my graph. So then I'm going to go to the Insert menu, and I will insert a chart, and that will create my graph for me. There's also a little chart button that looks like a bar graph on your toolbar that you can use for that. So once you have the graph sitting in front of you, there are two menus there that you can use to select the type of graph you want. In this case, you want a scatter plot. And then you can customize, you can use the Customize menu to make sure that you have titles and labels, and you can add in a trend line. So I'm going to show you what that looks like in the next slide. So here I am. I have my data highlighted, and I have created my graph. And I noticed here that I have the protons on the Y and the neutrons on the X. So I would want to switch those two axes. And I can do that by just switching my proton and neutron columns. So I can just grab my neutron column and move it over to the other side of my proton column, and that will automatically switch the axes in the graph. When I first made the graph, it was a line graph, and I needed to come over here and change it to a scatter plot. And then from there, I can go into the Customize menu, and I can put in a trend line. So I did that in my next slide. So now I'm in the Customize menu, and I want to put a trend line here to do a line of best fit to show the pattern in the data when you plot the neutrons and the protons. So to create a line of best fit, you go into the Series menu, and you just check off the box that says trend line. And there are different types of trend lines, so you can play around with the types until you find the line of best fit that fits your data the best. And then you have your nuclear stability graph with a line of best fit. And that's actually a pretty famous graph. It's called the band of stability. So it shows that when you plot the number of protons on the x-axis and the number of neutrons on the y-axis, you get a nice pattern of points that show a line of best fit, which represents, the line of best fit represents the proton to neutron ratio of stable atoms. So from this, the band of stability is the region where all the stable nuclei fall when you plot the number of neutrons versus the number of protons. So in your lab, you were given a list of stable nuclei, and you should have graphed them, and you should have found a nice line of best fit. And the slope of that line would have been a neutron to proton ratio of 1.5 to 1. And that is called the band of stability. Any isotopes that you graph on this graph, if you plot the points and they fall on the band of stability, the isotope is most likely a stable isotope. So I have a couple of examples here. First, I have the isotope neon-20. It has 10 protons and 10 neutrons. So if I look that up on the graph, 10 protons and 10 neutrons puts me right there, right smack on the band of stability, right on the line of best fit. So that is a small isotope with atomic number less than 20. It has a 1-to-1 neutron to proton ratio, and it lies right on that line of best fit. So it is a very stable isotope. It has 1 neutron for every proton. Neodymium 100 has 60 protons and 40 neutrons. So 60 protons, 40 neutrons, puts it down here below the line of best fit. So there's only about 0.7 neutrons for every 1 proton here. So if I were to plot the points and find this isotope, I would find that it is below the band of stability, and it's neutron poor. It doesn't have enough neutrons to reduce the proton repulsion. So it's not a stable isotope. Therefore, it is not fitting on this trend line. For tin 140, tin has an atomic number of 50, so it has 50 protons, and it has 90 neutrons. So it's got a lot of neutrons, about 1.8 neutrons for every 1 proton. So it is a neutron-heavy isotope. So it means that it is unstable. It is not a symmetrical nucleus. It has a lot of neutrons, and the nucleus is starting to get too big for the nuclear force to hold it together with all those neutrons in the way. So 3 different isotopes. I just plotted them on this graph, and I looked to see if they fell on this line of best fit, which is the band of stability. And if they do, then it's most likely that they are a stable isotope. And if they do not fall on this trend line here, then it is not likely that they are stable. They are probably unstable. So some isotopes are just too big. They're so big that the strong nuclear force can't hold them together. So astatine 215 is a good example of this. It has 85 protons and about 130 neutrons. So that puts it just out of range of the band of stability. So it does have a 1.5 to 1 proton to neutron ratio, but because its atomic number is greater than 83, it is just too large, and it has too much proton repulsion and not enough strong nuclear force to hold it together. So any isotope that has an atomic number greater than 83 is most likely in this situation. It just has too many protons, too many neutrons, it's too big, and it can't hold itself together anymore. So it is not stable. So why is this an important thing to learn about in chemistry class? It's important because unstable nuclei are radioactive. So all isotopes with atomic numbers greater than 83 are radioactive. And radioactive isotopes release harmful ionizing radiation. And that radiation can damage or kill living tissues. And if you are damaged by radiation from radioactive materials, your tissues can have mutations that can lead to cancer over time. And 85% of all isotopes are unstable and radioactive. So there are a lot of radioactive materials around us in the world. We are exposed to them on a regular basis. They do have an impact on our health. So it is important that we learn about this. Also, radioactivity and radiation have been used as tools to treat cancer, to detect things that we can't see, to create weapons, all sorts of tools and equipment and technologies use radiation as part of their purpose. So it is important to understand why things are radioactive.